So, let me spend some time on the results of Fourier series. Now, the intention is to get the magnitude of the harmonic components in the voltage on the DC side and also the magnitude of the harmonic components in the current on the AC side. Okay. So, some results may be useful in trying to compute the harmonic components. So, what we try to do here is consider a periodic waveform. Please note whether it is the AC side current or the DC side voltage, they are periodic waveforms. Now, we can say that all have a period 2 pi. It may have a period which is less than 2 pi, but 2 pi is still a period. So, if it repeats every every 2 pi radians, so then we can say that it is a period. Okay. So, for our purpose, we will consider all our waveforms to be periodic with period 2 pi radians. Okay. So, I will consider Fourier series of a periodic function So, I will not explicitly state what is that quantity I am considering, voltage or current. I will just use the general function f, which is a function of omega ot, of a periodic function with period 2 pi in radian is. So, this Fourier series is actually given by a series, it has infinite number of terms. So, the Fourier series is like this: A0 divided by 2 plus sigma over, I use the notation h for harmonic, over h from 1 to infinity of A subscript h cos h omega ot plus B subscript h sin of h omega ot. So, this is the Fourier series. Now, we will not get into the theoretical aspects whether the Fourier series converges, and if it converges, whether it converges to f of omega ot. So, we will assume that it does converge and converges to f of omega ot. I mean, we will just, as I said, we are just going into the results directly. So, we will use the results, we will not get into the theory behind this, okay. That is not part of this course. Okay. So, the intention is to get expressions for this AH and BH. So, if I take AH, so the result is like this: AH can be obtained from the given periodic function f of omega ot. It is 1 by pi integral of f of omega ot into cos h omega ot with respect to omega ot. So, I have to integrate over one period. So, I can choose any arbitrary lower limit, c is any arbitrary real number. So, I have to integrate over one period. So, the upper limit should be c plus 2 pi, and this is applicable for h equal to 0 also, then 1, 2, so on. So, for all possible values of h including 0, and BH is, say, when h is equal to 0, I get A0, A0 is the first term. Okay. So, BH is 1 by pi integral f of omega ot sin h omega ot d omega ot, and again integration can be between any two arbitrary limits provided the difference between these two limits is 2 pi. So, it can be any arbitrary c as the lower limit and the upper limit will be c plus 2 pi, and this is applicable for all values of h. Now, h does not take a value 0 here. So, it is 1, 2, 3 and so on. Okay. So, if I take the first term A0 divided by 2, Now, if you look at the expression, so you have to look at the expression for AH with h equal to 0. So, if h is equal to 0, what happens to cos h omega ot? 1. So, if you take 1 by pi integral of f omega ot with respect to omega ot between these two limits, what do you get? It is 2 times the average, because it is dividing just by pi. So, if you had divided by 2 pi, you would have got average. So, A0 by 2 is the average value of f of omega ot. So, this is average value of f of omega ot. Now, in power systems, we do not work with peak values, we normally work with RMS values. Okay. So, we are interested in what is happening to the fundamental component on the AC side. Say, what is important on the AC side is fundamental component, what is important on the DC side is average component. Rest are unwanted things. Please note that on the DC side, we only want the average value, all others are unwanted. On the AC side, we only want fundamental, all others are unwanted. Okay. So, if I take the RMS value, that is the root mean square value of fundamental component of f of omega ot. So, what is this RMS value of fundamental component of f of omega ot? So, can I write that, say, fundamental corresponds to h equal to 1. See, fundamental means it is the values obtained from this AH BH expression with h equal to 1, just as I got average with h equal to 0. So, it is equal to A1. Are you familiar with this? Can I relate the fundamental component RMS value of f of omega ot and A1 B1? So, it is A1 square plus B1 square by 2, this is taken under square root. So, this is the fundamental component. Now, similar to fundamental, I can get even the harmonic component, that is corresponding to h equal to 2, 3, 4, so on. So, RMS value of, we call what is known as hth order harmonic component. Hth order harmonic component of f of omega ot. So, this is similar to fundamental, only thing is in place of A1 I have AH and in place of B1 I have BH. So, it is under root AH square plus BH square divided by 2. So, please note this is applicable for h, say for h is equal to 1 we say fundamental, see the name fundamental is for h equal to 1. For h greater than 1 we say harmonic, that is the point. Okay. Fine. Now, sometimes it is easy to use some other Fourier series other than this trigonometric, this is known as trigonometric Fourier series, and there is another equivalent form which is exponential. So, the exponential Fourier series is like this: sigma ch. So, to explicitly indicate that ch is a complex number, I put an arrow over that. Okay. ch exponential of j h omega ot. So, this summation is taken over different values of h. What are the values of h? Do minus infinity to plus infinity. So, it is minus infinity to plus infinity. So, here ch is the coefficient which is appearing in the Fourier series. So, ch can be obtained from the expression for the function f of omega ot. So, it is 1 by 2 pi, I will straight away give the answer, integral f of omega ot. So, do you recall exponential of, do you recall minus j, yeah, it is minus j h omega o t d omega o t. So, the integration can be between any two arbitrary limits provided the difference between the upper limit and the lower limit is 2 pi. Now, this is just an alternate series which is equivalent to the trigonometric series. Now, sometimes this is easy to manipulate, sometimes the trigonometric is easier to manipulate. Okay. So, but many times the problem is a priori we may not know which one is easy. Only after trying both, many a times after trying both we will come to know, okay, one was much easier than the other. Okay. For the sake of completeness I am giving both. But can we relate these coefficients in this exponential series CH to the ones in the trigonometric series AH and BH? So, if I take for example C0, what is C0 in terms of the trigonometric series coefficients? A0 by 2. Yeah, you have to just look at the expression for this CH and then expression, look at the expression for C0 and A0, then you will easily see that C0 is A0 by 2. And since A0 is real, C0 is real. Though in general CH is complex, C0 happens to be real. Okay. Then if I take any other CH, say if I take H equal to say 1, 2, 3 and so on. So, can I relate CH, AH, BH? So, can I get an expression for CH in terms of AH and BH? So, it may not be straightforward, one can show this. So, I will just give the result. It can be shown that this is equal to AH minus J times BH divided by 2. So, this expression is applicable for positive values of H.
Also, we can write AH in terms of CH.
Yeah, we can do that. Yes, yes, we can do that. Okay. Now, in CH, H can be either 0 or positive or negative. So, we have taken C0 and positive values of H. We can also consider negative values of H in CH, of course. So, when it comes to the subscript H in for C, H can be positive as well as negative. Okay. So, can I relate this to the coefficients AH and BH? So, here also I can relate, but it is not AH minus JBH or it is not in terms of AH and BH, because H is negative. See, what I am trying to do is I am trying to do this for negative values of H. So, H equal to minus 1, minus 2, minus 3, so on. So, in this case, if I take AH is not existent, A minus H, A subscript minus H. So, it is actually A subscript minus H plus J times B subscript minus H divided by 2. These things can be derived, I am just giving the results. So, that gives the relationship between the coefficients of the exponential series and the coefficients of the trigonometric series. So, if I take the RMS value, so similarly I can take the RMS value and try to express it in terms of CH, just as I did for the trigonometric series. So, RMS value of fundamental component of f of omega o t. So, can I write it in terms of CH? In fact, when I say fundamental, it is in terms of C1, it is in terms of C1. So, no, if you recall, or it may take some time to find out what is RMS value. So, if you recall, I do not know, you have seen this result, it is the absolute value of C1. Please note, RMS value is always a positive real number. Okay, it is a positive real number. So, you have to take the absolute value of C1 multiply by root 2. See, the contribution to the RMS value of fundamental comes from both C1 and C minus 1. It comes from both C1 and C minus 1. Okay. So, similarly, if I take any harmonic component, so RMS value of Hth order harmonic component. Yeah, if you are not familiar with these results, you can just verify these things. Please verify if you are not familiar with this. So, if you have never studied this earlier, you have to do it. Okay. So, you need to just do simple, integrations and try to show that these are the expressions for the fundamental RMS and Hth order harmonic component RMS. So, similarly, for the Hth order harmonic component, the RMS value is root 2 into absolute value of CH. So, again, if I take any Hth order harmonic component, H is of course, see when I say Hth order, H is positive. When I say Hth order, H is positive. So, the contribution is coming from both CH and C minus H. Okay. So, I can use either the trigonometric Fourier series or exponential Fourier series, but if you observe, both involve taking taking the integral over one full period, that is 2 pi radian, whether it is AH, BH or CH. Now, many a times the waveforms are so complicated, longer the duration for which you have to integrate, it is more laborious. So, there are some shortcuts or some easy ways to get the expressions for AH, BH, CS. So, essentially we are trying to calculate the values of AH, BH or CH. I can use either one. So, if I can somehow reduce the duration for which I integrate, then I can quickly get the values. So, it is possible when these waveforms have some sort of symmetry. Okay. So, there are various forms of symmetry that a periodic waveform can have. So, depending on that, there are simplifications. Okay. So, I will just start with some definitions. So, I will get into the details in the next class. So, all of you have heard of this odd function. So, we say that a function f of omega ot is an odd function. So, what I want to say is, okay. So, let me give a precise definition of this. F of omega ot is an odd function. So, that actually means that f of minus omega ot is minus f of omega ot. Similarly, there is one more type of symmetry, f of omega ot is an even function. So, the definition of this is f of minus omega ot is equal to f of omega ot. So, if a function is odd, then we get some simplification. If the function is even, we get some simplification. There are other types of symmetries, for example, half wave symmetry, quarter wave symmetry. So, due to all these symmetries, we get some simplification in the evaluation of the integral for the AH or BH or CH. Okay. So, we will look at all these simplifications in detail in the next class. So, I will stop here.